Hello guys, today we want to understand a problem in the calculus of variations. So I'll begin with a brief about what is this topic about, and there's an interesting problem which follows. So in calculus of variations, uh, we we get a mathematical tool to uh, to solve something that looks very similar to maxima and minima. So there's what you call optimization problem. But instead of maximization or minimization of a function, we that's what is called as the extremal. We find the extremal of a functional. And loosely speaking, what it means is a functional is a function of functions. Uh, I think you would have seen this problem of finding the shortest path between 2 points. So you look at all kinds of paths and you want to find what is the path that minimizes a certain function, a certain aspect, like let's say the length, right? So each path is a function. So it is loosely speaking, a functional is a function of functions. Function of functions. Okay, so having said this, let's look at this very popular problem called the hanging cable problem, hanging cable chain, whatever you call it, hanging chain. So you want to identify um, the shape. Basically, there is a cable chain which is a fixed length chain, and that fixed length is what is the constraint in the problem. So given this fixed length, what is the shape? What is the shape? So that's the problem. So a little bit of physics is in store here. So basically, we solve for the shape of this cable, which is constrained, meaning that it is fixed with these two pillars, and uh, the length remains same. So it's something like how one solves the linear programming problem. So you have an objective function to maximize or minimize something and subject to certain constraints. So same here, we want to uh, minimize something. Here in this problem, we want to minimize, but in general, we find an extremal. So it turns out that whether it is a minimization problem or a maximization problem, the same kind of a differential equation comes up. So uh, as I said, I'll get back to the physics of the problem. So the this system that we have of forces here is in a static equilibrium, right? So it's in a static equilibrium, which means there is no net force acting on the system, and there is also no motion. That's what I said, static. So in the absence of any physical external force, what happens? The the tends to system, meaning system of all the forces acting here, tends to move in such a way that we get a state of lowest potential energy, right? So there is a tendency of the components involved, that is the whole system, to move in such a way that the it attains the lowest possible potential energy. So we understood the physics of it. So uh, given this kind of a problem, we can place it in the context of calculus of variations, because the length being constant means that it's a constraint in the system, and we are trying to uh, get hold of potential energy, and through that potential energy we have an integral. So in that integral we have the functional uh, expression, and hence we get a corresponding what we call Euler differential equation. So that's um, something one has to read through theory. So given any such constrained variational problem, one looks at a corresponding Euler equation, or more precisely Euler-Lagrange equation. So we can have another video about the derivation of this, which we can do leisurely. But right now, we'll assume this, which I'll talk in a few minutes. So let again let us draw something like this. So let this point be a x1 y1. Let's assume, or rather draw this diagram in accordance with this, the horizontal reference line being the x-axis, and from this reference line we have coordinate a as x1 y1, coordinate b as, sorry, coordinate b, which is this tip, as x2 y2, and between this is this chain hanging. So we need to finally get the shape of this uh, cable, and again there is a idealized condition that we ignore that it's having the three-dimensional cable. Let's idealize it as a one-dimensional linear uh, I mean one-dimensional geometric object, and let us assume that it has some fixed density. Let mu maybe it's kg per let's say meter per unit length. It has a certain density. Also, uh, yeah. So we can look at this. I'm sorry, it, I thought it should be a straight line, but anyway, this is a straight line. You have to assume it's the origin. Now, so um, if ds is the arc length here, arc length, let's say any infinitesimal arc length is ds, and then because I said that the this idealized one-dimensional cable has density mu kg per meter, so the total mass is mu ds for of the arc, this cable element, small element. Okay, so then the potential and energy with this horizontal line being the axis of reference is given by Pe equals to mgh. Okay, so this um, because my mass is mu ds, I can write it as mu ds times gh. And so this is just for this arc length element. So now what we shall do, the total P, the total potential energy of the system is going to be integral from A to B, this mu ds, and then because this height is uh, okay, let's take that at this point it's y, so it's a variable, so we can take it as y. So along the curve, uh, at any given point of time, uh, at any given point of position, let it be pxy. So the height will be uh, y. So we have mu dsy. So this is can be, because these are constants, mu is a constant, gravity is a constant. So we just have y ds from A to B. So uh, now I think we'll do a small manipulation. She'll write it as mu g x1 to x2, of course, because we are integrating with respect to dx. So y, we will just write the y ds as the rate of change of arc length element, and then integrate with respect to dx. So now your we can utilize the fact that arc length derivative is 1 plus y dash square the whole root. So this is your ds by dx. Therefore, v equals mu g x1 to x2 y times 1 plus y dash the whole square root dx. So yeah, so it's a little sloppy here. I did not yeah, I should not have written the integral right away here. uh, it's this, the the integration process with respect to dx. So only after I do this manipulation, so this is not quite right, but here I've done that manipulation as the potential energy being mu dsgh can be written as mu g times y ds by dx times dx when I introduce the integral. So now this, let me write it as some script A equation, and we are now in a position to apply calculus of variations because we are having the integrand with an unknown function y. So among all paths that the chain takes, for what path or for what y is equal to f of the independent variables is the potential energy minimized. So that is, we have a function of functionals here. Okay, that means we have a functional. So your functional here is mu g y, because it doesn't matter whether mu g is inside the integrand. We took it out because it's those are constant terms. But overall, we have the right hand side representing the potential energy, uh, involving the variables y and y dash. So explicitly we don't have any x term, and therefore there is a theory which I alluded to earlier. The corresponding Euler-Lagrange equation becomes f minus y dash partial of f with respect to y dash is a constant. With that, let's say it's a k. So this is your Euler-Lagrange equation. We'll substitute for f, which I've given just below my script A, and so I'll simply write for f mu g y 1 plus y dash the whole square power 1 by 2 minus this y dash times the partial. Just observe that when I differentiate, uh, we do get this constants mu and g, and 2 times y dash divided by 2 root 1 plus y dash the whole square. And that is going to be a constant. So I'll just cancel this 2. So what do we get is y times 1 plus y dash the whole square minus, um, observe what we are doing here is, you have mu g in the first term as also mu g in the second term. So I'll ignore it. Not ignore. Basically, I plan to take it out to the other side. So I'll just take the other parts. So minus y dash the whole square equals to some other constant. I'll tell you what that constant is. 1 plus y dash the whole square, the whole power half. So what is it? What is that happening is that, uh, so I've just jumped one step. So if this denominator term is taken as the LCM, then you have root of 1 plus pi dash the whole square, and yeah, so and then this mu g goes to the other side as k divided by mu g. So this c is nothing but k divided by mu g, and this root of 1 plus pi dash the whole square is there. So yeah, so because I multiply this root with this root, I have I have now got power 1. Observe here, I had root half. I multiplied this guy here, so I get root power 1. So that I'm justifying my step which I've jumped. So here c equal to k by mu g, the new constant I've introduced. So now, um, if you see observe properly, this plus y dash square. So this is just no, it's not a dash, so don't get confused by this. So let me remove this guy. Yeah. So if you just observe y dash square here is with a plus sign, y dash square here is a negative sign. So I'm going to strike them off. Okay. And so what is left is y square minus y square minus. Okay, why did I do y square? Sorry. Again, I'm tending to jump steps. What I can do is, so this left side is left out with y equal to c root of 1 plus y dash whole square. I square both sides. So y square equal to c square 1 plus y dash whole square. So which means y square minus c square equals to, this is c into 1, c square into 1 has come this side. What is remaining is c square into y dash square. So now, so basically, let's hang on and see what exactly are we doing. We're solving for y. Basically, I said a y is an unknown function because it's we want to catch hold of that function which minimizes the potential energy. So we are solving for y, and we are approaching a neat differential equation. So this implies, I'm sorry, I'm sloppy in writing this. This implies y dash uh, y dash square equal to 1 by c square y square minus c square, which means y dash alone is just 1 by c root y square minus c square. Now just separate the variables and integrate. So separating variables and integrating both sides, what we get is, I'll write the appropriate differential equation. Dy by dx, it means here we have dy by dx, so I'll rewrite what it is. Dy by dx is 1 by c root of y square minus c square, which implies that was my original thing. Dy, I get this y square minus c square. Remember, I'm separating variables, equals c dx. So I put an integral sign both sides, and I introduce another constant of integration. So guys, we know this is a very easy integral. We know that this is simply cos hyperbolic function here coming up. So this implies cos hyperbolic inverse y by c equal to, what is this guy telling us? Cx plus b. In other words, y by c is cos hyperbolic of cx plus b. Or y is equal to c times cos hyperbolic of Cx plus b. So this is the path that we are looking at. So this is can be seen as a catenary, and therefore the hanging cable problem leads to the shape being a catenary. So that solves the hanging cable hanging cable or chain problem. So there are many other interesting problems like the isoperimetric problem, etc., can be solved by calculus of variations, which we can take up in some other session. Thank you, guys.